Okay, Assalamualaikum and good afternoon. So today we're going to continue with our lectures. As I mentioned in the last lecture, uh, we are supposed to go into some kind of approximation methods. One of the things that we thought of doing before this was your WKB methods. Okay, but I decided I will skip this because this is essentially just an ordinary solving a Schrodinger equation, time independent. And I think you have enough experience of how to solve this. The only thing over here, probably you need to get used to the idea of array functions. So you can actually look at one of the books, which is on the band and Avishai. So they have a small section on chapter, I can't remember precisely which chapter, chapter 4 or something, on approximation methods. So the first one is essentially on, well, the second section. Second section is basically on WKB methods. And this is quite brief. You can look for other books like Libov, which goes a little bit more detail. Okay, but I think I will not go into this, so I will jump straight into perturbation theory. Hopefully we'll buy some time for other topics later on. Right. So the first one would be to look at. I have not. I'm not sure whether I've uploaded this in the Putra Blast. I will check later on. Okay, but this is essentially I'm doing the same sort of structure from Sakurai's book, which is now this supposed to be Sakurai chapter 5. Okay. So let us begin with the simplest case that one can think about is essentially looking at a two-state Hilbert space, and the first you have a time-independent Hamiltonian, and the time-independent Hamiltonian is broken up into two. One is the unperturbed Hamiltonian, so this is unperturbed, for which you already know what the solutions are. Okay, so we can find out what the eigenvalues are. The eigenvalues are given by En naught. Okay, and then you know what the eigenstates are, which is labeled as N naught. Okay, this is for the unperturbed Hamiltonian. So this is assumed to be known. Okay, the one that makes the problem slightly more difficult is a term over here, for which is considered as a perturbation to the H naught that we had earlier. Okay, so in other words, your lambda is going to be what we call a perturbation parameter, and V is your perturbing potential, and we need to find out under this new Hamiltonian what its eigenstates are. So your eigenstates now labeled as N, different from N naught. Okay, and what is your new eigenvalues En? Okay. So one of the things that we also expect, if you take the limit of lambda goes to 0, then one should be able to retrieve back the solutions of the unperturbed problem. So in other words, one can always do a check whether your solutions to this equation is actually the right one by just looking at the limits. Okay, so we'll start off with a simple case of the two-state problem, which is essentially it's like your spin-Hilbert space kind of thing. So you have only two different bases to the systems. So in this particular case, I can now write, well, if I have your H naught, then this can be just given by I would need to be careful about the terminologies here. So E1 naught. So I completely forgotten the symbols. Okay, E1 naught, 1 naught, and then E2 naught. So you can think of this just like your spin up. So this is a spin up projection operator, spin down projection operator. So essentially in this particular case, this is a diagonal matrix. Okay, but now we have terms coming from your lambda v, which should make your Hamiltonian, the total Hamiltonian, not to be diagonal anymore. Okay, so in other words, you have terms coming as off-diagonal terms, which is written in terms of lambda v12, 1 naught, 2 naught, and lambda v21, 2 naught, 1 naught. Okay, so if you essentially expand this Hamiltonian in terms of this unperturbed basis, then it becomes this 2 by 2 matrix given here. The other thing that we need is that you need to have your Hamiltonian to be Hermitian. Okay, so in other words, this has to be related to this by a complex conjugate. Okay, so then we can set the following. In this particular case, we make them to be real. So in other words, by right, we just have that. Okay, but now we set the parameters to be real, so this is just the same thing. Okay. This is just a remark that you can essentially do this because really if there is a different if there's a parameter that sort of makes this thing to be complex, you can just remove the phase by putting a relative phase between the basis states. Okay, you can always do that in this particular case. Right. So now what one could also do is to write your 2 by 2 Hamiltonian matrix using your polymetrics. I've forgotten all the names. Your polymetric. So remember that you can always expand any 2 by 2 matrix in terms of this expansion. Okay. The only thing that we try to avoid in this particular case is to remove the one which involves sigma 2, because sigma 2 is, if I'm not mistaken, I can't remember precisely which one is positive and negative. I think it's this one. So we do not want to have this because we want to maintain the fact that this is going to be real elements. So we remove sigma 2 from the dot product here. So the only terms that's appearing is coming from sigma 1. Sigma 1 is simply 0, 1, 1, 0, and sigma 3 is the diagonal matrix 1 minus 1. So you'll find that, okay, this is now given as a totally real 2 by 2 matrix. Okay, and one can easily solve what the eigenvalues are. Okay, so you just use the characteristic equation for this matrix. So essentially you take the determinant to be equal to 0, okay, for this matrix, H minus lambda I, and essentially you get a quadratic equation in terms of lambda, and then you just simply solve that quadratic equation. Okay, set it to equal to 0, and then you find out your energy is given by this. Okay, and remember this is really related to the elements of the matrix earlier given here. Okay, and you can identify, for example, that A naught plus A3 is just your E1 naught. Okay, and then A naught minus A3 here is your E2 naught, and then your lambda V12 is this A1. Okay, so the corresponding energy eigenvalues for the perturbed case is going to be given by this solutions of the quadratic equation. Okay, and this is written in this way. So you can see the behavior is actually given by the departing from the unperturbed case is given by this factor of lambda squared V12 squared. Okay, so one of the things that we always want to do for perturbation theory is that you want to make this perturbing parameter to be small. So the way we do this is to think of this term is much bigger than this term. Okay, so in other words, we have this condition that one needs to have in order to make your perturbation theory valid. Once we've done that, and so this is small compared to that, so I can sort of bring out this particular factor out. So you can see that this becomes 1, and then this will be divided by your E1 minus E2 naught square. Okay, and then you can see that this is going to be a parameter which is much less than 1. Okay, and for that particular case, you can always approximate your square root there to be given by this Taylor series. Okay. So this is the thing in full, and you'll see that in this particular case, your E1 is given by the one with the upper sign. So if this is just 0, then you can see that E1 plus E2 plus E1 minus E2, so that your E2 will cancel out, and then you get your E1. Okay, and then for the lower sign, will give you the E2. Okay, so now what happens is you have this perturbing what we call factor over here. So I can start using the what we call approximation we had earlier, this thing, and for first order kind of treatment, then your E1 will be just related to E1 naught, by this perturbing term. Okay, and similarly for E2 will be given by this perturbing term. Okay, so more or less this is quite simple enough because it's a two-dimensional Hilbert space problem, so you can always solve it. In fact, you can solve it to many orders if you want to. But you can see sometimes you don't really have that two-dimensionality of the Hilbert space. Then one needs to be a bit more general in this particular case. So that's the next thing that we want to do. Okay. So let's now just consider much more general where your states, your basis states might be, even infinite for that matter. Okay. So let's do this. So again, we assume this unperturbed Hamiltonian eigenequation given by this, and this n naught, your eigenstates, will form a basis. So in the context of the unperturbed Hamiltonian, the basis states will obey this completeness relation given by here. Now let's consider, excuse me, so let's consider the case where you have the perturbed situation. So now we proceed. There will be a new eigenstate n, okay, that satisfy this eigenequation. Okay, just like the case of the 2x2 case. Okay, but now you have a much more general, many level states coming in. So again, we expect somehow there will be some changes to the energy eigenvalues, and you can write the change in the nth eigenvalue by delta n. Okay, and then substitute this into the eigenequation. Let me just see over here. So I can now write this, for example, as h naught plus lambda v n, and I want to use delta n here, so I will have my delta n, and to cancel off this minus e naught in your delta n, I will put a plus. Okay, so I can now rearrange this equation. Okay, rearrange in such a way that, okay, I will have en naught over here, and then I'll bring your h naught on the other side. Okay, and that will give you this, and then your delta n over here will bring to the other side, and it will give you this. Okay, so it's just rewriting the eigenequation. Now if we look at this, okay, on this side, essentially the one with the bracket essentially is something you already know. Okay, because this will be the unperturbed Hamiltonian, and this will be the unperturbed eigenvalue. So it is probably tempting just, okay, if I want to find the solution to this equation, which is equivalent to the perturbed theory eigenequation, I can just simply bring this, where this is just something that is already known. I can bring it on the other side. So one has to remember that this is not really a number to start with. This is an operator. So in other words, one has to be able to define what that means. Okay, but let's suppose we do that. We bring on the other side, then I'll be able to express your eigencat n for the perturbed case to be this operator divided by this operator times cat n. Okay, so unfortunately this is not as simple as that, because when you have this at the denominator, there's a possibility that this cat n might have a component in the n naught direction. Okay, and when that happens, when your h naught acts on n naught, it will give you en naught. Okay, so en naught minus with this en naught from this action of the h naught on the direction of n naught will give you 0. But you bring it on the other side, then you get 1 over 0, which is not the thing that we want. Okay, so it must be done in such a way that this component must not be there. Okay, so how can we do this? So let us first note this particular property. Okay, so you remember the operator over here will have the one at the top, the numerator, and then this thing at the denominator. The one that seems to give you a problem is the one at the denominator. But let's look at the one at the numerator. What does it mean? This thing acting on n, and suppose there's an n naught direction. Well, in that particular case, it gives you 0. So if you just simply make this what you call inner product with n0, so you find that okay, n0 lambda v minus delta n, remember that this is the same as this operator. Which one is that? Yeah, sorry. This one is equals to that. Okay. Then I'll be able to rewrite your operator here given by this operator by substitution here. So then this will have en naught, which is just an eigenvalue, but h naught. H naught here, remember that you know how it acts on n naught, but once you know how it acts on n naught, you automatically know how it acts on the eigenbra, okay, because your h naught is Hermitian. Remember that maybe I should write this thing down just for you to remember. Once you know how it acts on this, okay, then automatically you know how a dagger acts on that, on the eigenbra, or in this eigen. It's not even eigen. In this case, in this particular dual state. Okay, so you know this, automatically you know this. But now the fact that your h is Hermitian, so you know how h naught acts on your n naught, and that should give you en naught, which then trivializes to be equals to 0. Okay, so in other words, not only we are avoiding, if you have the fact that this cat vector, okay, is being sort of projected in directions away from this n naught direction, then you have no problem. Okay, so what do we do in this particular case is to define a projection operator called the complementary projection operator. So we just simply remove from the identity this component that sort of find things parallel to n naught. So you remove it away, then you find all the components which is not in parallel to this. Okay, so here there is a sum from going from k not equals to n and over all possible k. Okay, so it projects out all the n naught direction. So we can now make that operator now by first allowing this operator acts on the state. So before it what we call acts on the state that is the state n previously, for example over here, then this will project out all the n naught directions from that state. But once you do this, so this, remember, there's an operator here, and this is also an operator, which is a complementary projection operator. Now I can now write this complementary projection operator in terms of this, and this is in terms of your unperturbed eigenstates. Okay. So the only thing that's not there is the case of n naught. Okay. So in other words, this being eigenstates of h naught, I can now sort of act on this phi n to give you this value ek naught. Okay. So in other words, we have now an expansion of these two operators. Okay. What else? Okay, the other thing is, of course, if we look at the lambda v minus delta n, since this operator acts on this, if there is a direction of n naught, it will give you 0, right? The previous thing that we had here. Okay, so in other words, if I also add this complementary projection operator, it doesn't do anything. Okay, so I can replace your phi n, your lambda v minus delta n by phi n lambda v minus delta n. Okay. So in other words, we are almost there in some sense, because what happens over here, remember our technique was to think of this operator is divided by this operator, right? And then you'll be able to get your your perturbed states. Okay. So it's tempting to do that together with this complementary projection operator. Okay, so, which sort of projects out all the problematic states. Okay, but this one is not good enough, because why? Once you put your perturbing parameter takes the limit up to 0, that means you go back, by right you go back to the unperturbed situation. You require that your solution over here should be approximating the unperturbed case. But if you do that over here, you get essentially equals 0. So in other words, this kind of solution is not good enough. So we need to do something else. Meaning, once you have this, we also need to add back in a component which is proportional to n naught. Here are all the components which are not in parallel to n naught. So it's missing one component, which is the one proportional to n naught. So in other words, the right solution would be something like this. Okay, So here is the case where everything is perpendicular to n naught, and here you have something which is parallel to n naught, and that would work. And if you take lambda goes to 0, this will go to 0. Okay, and lambda goes to 0, so this part. So let me just write this. This will go to 0 as lambda goes to 0. And this one, we'll make sure that when lambda goes to 0, this goes to n naught. So in other words, the condition that we need over here is the limit of this, whatever coefficient there is in front of this, that should be equals to 1. And if you check, if I were to take the inner product with n naught, okay, so what's going to happen, the terms here will not be 0 because you have n naught, and you're left with Cn lambda. Here, n naught will be contracting with this, we'll take the inner product with something which is orthogonal to n naught. So in other words, this goes to 0, and then you actually have this. Okay, so so what we're going to do in this particular case is to sort of set this so-called coefficient in a way that it's convenient for us to do perturbation theory, and we set this to be equals to 1. Okay. Now, if we do so, in other words, what's going to happen, we cannot use this kind of condition anymore, okay? Because you have this instead of n to be equals to 1, you have this to be equals to 1. But that's a small matter because we can later on shift this what you call product to a different value. So let's look at what happens when we have this projection operators. So some of the things that we have already seen, that one can get rid of the problem of this thing at the denominator by just inserting this projection operator. Okay, so now how do we make sense of this? Perhaps one should be careful to think of this to be, no, because operators are being multiplied here. Well, actually it's been divided, but no, you can think of division to be just an inverse operation of the multiplication. So one should be thinking this one is really this thing, okay, but putting the projection operator here will just make the problem for the n naught case with the cat to be what you call disappearing, okay, to be eliminated. But you also need to make sure that if you consider action of the operator on your graph, okay, so in other words, the better the better operation that one should have is this one, where you have your projection operator in front and your projection operator at the back. Well, actually this one is at the back and this one is in front, okay. So that we shall use it in a way which is contextual to the equation that we are considering, okay. So if you have both n naught in the cat side and the also and not in the brass side, then you actually use this particular operator, so to speak. But for now, we can just think of, for example, acting on this cat. You can just simply use your this one, okay? And want the sort of hand waving kind of thing, so I can always replace this by that. Okay, so that is equivalent to this, and in some cases also equivalent to this. Okay, so it's not so. I mean, it depends on the context of how you write the equation down. Right. Now, if you take again as previously, if you take the case of the previous equation that we had earlier, is that let me check. I thought I had it somewhere. Yeah, that's here. No, not this one. Where's the equation? Oh, yeah, it's this one. Okay, so you have to remember that we have this to be equal to 0, right? So in other words, we can actually use that. Let me go down. You can use that. So in other words, you have n naught, was it lambda v minus delta n naught equals 0. So no, that was not n naught. Let me just check back. That's n, right? Yeah, here. So it's n, sorry. So again, going up and down this page, so bear with me a little bit. So what we had previously was n naught lambda v minus delta n, and that is equal to 0. So we can start to rearrange this. For example, this is n naught lambda v n naught minus n naught delta n. Okay, now I made the same mistake here, sorry. Let me do this again. N naught lambda v n minus n naught delta n. But delta n, remember, is just the difference between the perturbed eigenvalue and the unperturbed eigenvalue. Okay, so it's just a number, so you can bring that out front. So this one becomes delta n, or I can rearrange this equation. Delta n goes to the other side, and essentially delta n is given in terms of this perturbing potential there. Okay. So in other words, this more or less tells you about the eigenvalues of your perturbed system. Okay. So all we need to do now essentially is to be able to, so this is not how shall I say, it's not a closed solution, because why? We still have the unperturbed state here. So if we could actually also get an expression of your your perturbed state in terms of the unperturbed states, then it will be easier. Okay. So over here, what we're going to do in order for this to be a closed, well, not a closed, meaning everything is written in terms of some known state. Okay. So one can essentially expand this to powers of lambda. Okay. So we assume that we can do that. So your zeroth order term for this perturbed eigenstate is just equals to the unperturbed state. And then you have the first order term. So this is unknown yet. Okay. And for higher order terms, you have your lambda squared. And again, this will be unknown. Okay. Similarly, for your delta n, we assume that we can also expand this in power series. So it will start with the first order term, because this already takes away the zero order term for this is just zero. Okay. So there you have again another power series in terms of lambda. And then you plug this thing back into this equation. Okay. So here you have a power series. Here you have your power series. So you're going to get a power series in lambda in both sides of the equation. And you'll be able to equate powers. Okay. So the first order term, the first order power of lambda here will give you delta n1 on the left hand side. Okay. And then, so this one. And then your right hand side will be given by your essentially, remember that this is the zero order term, but you take the dual. Let me just write the dual of things. This is n0 plus lambda n1 plus lambda squared n2. So this, remember, has to be, if you look at the equation here, okay, or maybe I don't need this. Okay, I just need that. Okay, sorry, I don't need it. But essentially, you know that okay, the thing that we need is this n0 term multiplying with the first order term over here. So that's why you'll get this n0v n0 thing for this delta n1. Okay, so this is from the right hand side, this is from the left hand side. For the next case, okay, then you'll see that okay, I need a lambda squared. So the lambda squared gives you this delta n2. And then for your thing on the left, sorry, thing on the right, I can use n1, okay, which has already a lambda, multiplied with this lambda. Okay, so in other words, what you get is a lambda squared. So you get the next term to be given by n0 v n1. And then you could proceed until you have, you know, the general term will be something like this. Okay. So finally, one should be able to write everything down in terms of your operators, in terms of your, you know, potential. Sorry, I'm getting lost for the words. Potential, but what one should be remembering is that we need to include the idea of a projection operator and also this. Okay, this comes from the earlier assumption that we can actually bring it in this particular form. Okay. So in the end, one can start solving it bit by bit. So for the first equation, we should be able to get your n1 in terms of that. So once you have n1, then you can plug it back in, okay, from the previous equation. Then you get the delta n2, okay, and then from delta n2, you can solve for your n2, what I call the cat n2, okay, and so on and so forth. So essentially, if you look at what's happening here is the terms keep multiplied by this projection operator, okay, and the ones that's involved in terms of numbers are things like this. So generally, the thing that you're looking at is this matrix element. So we're going to essentially rewrite your potential operator over here in terms of its matrix elements, which is given by V and K over here. And this matrix elements with respect to the unperturbed basis states. Okay, so V and K here is different from this quantity. Okay. Finally, let me see. We can rewrite in terms of this matrix element as follows. So you get your lambda V and N for the first order term here, and then your lambda squared will involve this sort of your what do you call this, non-diagonal terms. Okay, the non-diagonal terms is going to be divided by this eigenvalues, which is not going to be 0 here because you have t not equals to n here. Okay, and so on and so forth for higher order terms. And similarly, we can do this for the perturbed state. Everything is now re-expressed in terms of this vkn. The higher order terms will have something like this. Okay. And I think that's probably the thing should be able to solve the perturbed case in the general case. Okay. So what happens in this case, essentially you'll find the perturbing potential actually makes the unperturbed energy levels. Okay. So your Kn, for example, is saying that you have this potential sort of allowing you to go from one unperturbed state to another perturbed state. Okay. So here, for example, is going from the N state to the K state. And what else? Okay, usually we evaluate expectation values of V up to first order. And then for the states, you go to second order, okay, to include some change of what you call unperturbed states. Okay, and the energy shift between two levels, for example, given by this kind of terms, is symmetric in a sense that if you write your Vji squared over Ei naught Ej naught, okay, they are supposed to be equal. Okay, equal but in a opposite sense. One is going up, one is going down. So we have what you call energy shift of the two levels in such a way that initially is for example maybe this, okay, one goes up and one goes down. Okay, so I think I will stop there for today because the next thing was to talk about the normalization. So I will stop there and we'll take your attendance now. Right. Okay, are there any questions before we stop at this stage? Yeah.
Have you decided on whether you'll include time-dependent perturbation theory?
It should be in. Okay, let me just check with the book. I've taught these courses before and I did. Let me see, when is the time dependent one? Yeah, it should be in. Okay, should be in.
Okay, doctor.
All right. Okay, if there's nothing else, then I will check whether I've already uploaded that lecture notes and see. Okay. All right. Thank you, everyone. Bye.